So we're going to make a rectangle. That looks good. But I got a wall. So up here, I am just going to write the word wall. Now, I don't know about you. Most of the time, whenever I see a building, I don't see a fence right next to it. It doesn't make sense because the wall is there. You don't need the fence against the wall. So it tells you specifically, we're only using it for the other three sides. Okay, so 150 all the way around up to the wall. So from here to here to here. Okay, it'd be nice if I had some type of, oh, I do have an eraser. Whee. Okay, so if I got 150 meters total, I need a variable because I can change the size of the fencing. So let's make x as our variable. Do you think we should make it over the long side or the short side? The two long sides are the same. Long side, because otherwise it's not wrong, but it makes the other ones a little more complicated. Okay? So we don't need it at the wall. So now we have 150 total, but we already used up 2x. So say those x's were 10s. Okay, so if I had a 10 here and a 10 here, how much fence would I have left for my bottom part? 130. How'd you get that? The 150 minus the 2 10s. Well, instead of 150 minus 2 10s, how about 150 minus 2x? Okay, and ultimately what we're trying to do here is we're trying to find an expression for area. So take a moment, now knowing that I'm going to make my lengths x and my width 150 minus 2x, to write an expression for the area. Okay, see what you can do on your own.
So it would be...
You can write this in expanded form. If I don't ask you to distribute, I would just leave it in factored form. So in this particular case, what you got? What you got, Dylan? Okay, so how do you find the area of a rectangle, Dylan? Anytime, Dylan. How do you find the area of a rectangle? Width times height, or in this case, we're going to use width and length, but exactly. Okay. So length times width, base times height. So I've got a base here of 150 minus 2x. And I've got a length here of x. Just like that? Not quite, right? What do I need, Derek? And that is your algebraic representation of the area of that particular rectangle. Okay? So now the question is, what's the area going to be when x is 40? And unlike yesterday, they didn't give us a tool. So what tool should we use today?
Desmos.
So go to Desmos, plug in the 40, and find the area. And I would call this 2.21 practice. 2.21, yeah. Okay. In this particular case, it's going to put the 150 minus 2x and times x. Okay. How do I find my area? Just take 40 and dump it in there, right? Okay, so I want to leave this up here, so I want to duplicate it. So I'm going to duplicate it, click done, and change my x in the second one to 40s. So I can see that I got about a 2,800 square meters. That's a fair size yard. Okay, that's pretty big. So 2,800 meters. So let's go back and take a look at the domain. Okay, so in order to look at the domain, I actually want to look at the graph. So if I look at the graph as it is right now, that's not too easy to look at. Okay, So let's change it a little bit. So we already know that it goes up to at least 2800. So let's change our window just a tad. Back mouse. There we go. Let's change our window. So we don't know that that's the most amount. So 2800, probably a little bit bigger than that. Let's go up to like 3000 on the Y, not the X, the Y. Something like this. Okay. Oh, I only went to 300. My bad. 3000. It looks like that's a pretty good estimate, but I'm now going to need to move. This is kind of a pain. Let's see if we can figure out our domain a little bit better. So let's go back to the actual equation. No, not you. Okay, so can we agree that when we measure things, we can't have negatives? Okay, so we're going to set up two expressions here. Okay, so x has to be greater than 0. No negative, and it doesn't make sense to be equal to 0, so that's why I'm making it greater. And then I'm going to look inside my parentheses here, the 150 minus 2x, and I think we also need to agree that also must be greater than 0. So now I want you to take a moment. I already know it has to be bigger than 0, but it doesn't go on forever. Remember, our fence only goes 150 meters. Figure out what x can't be any bigger than. So solve this algebraic inequality right there. So we solve this just like a regular equation, right? So what should we do first? Minus 150, okay? So I got negative 2x is greater than negative 150. And do you remember when you divide by a negative what you have to do with the inequality sign?
Don't you flip it?
You got to flip it, okay? Because remember, 1 is less than 2. But if I divide by negative 1, negative 1 isn't less than negative 2 anymore. So that's why we flip the sign. Because by dividing by a negative, you're taking the smaller number and making it bigger. Okay? So in this case, I know x has to be less than 75. Now, there's a more elegant way to kind of connect all of this. So instead of saying x is greater than 0 and less than 75, we're going to say it's between. And the way we show between is with something called a component inequality, which we're going to see a lot more of. So between 0 and 75. Okay? And even 75 wouldn't make too much sense. Because 75 means I have my two 75-meter pieces of fence. Where are the kids going to play? Yes. You only got 150 meters, right? So the 0 and the 75 are the extremes. So unless you're having something really narrow, I don't know, maybe you can make it 70. And then, you have 2.5 meters, which is, kids could run back and forth a lot. Okay. That's about it. Not going to go side to side a whole lot. 2.5 meters, it's about. Dylan, how tall are you? 6'3". Okay, so Dylan's a little shorter than 2.5 meters. He's about 2 meters tall. So 2.5 meters is about a Dylan and a quarter. Okay, so that's how far a kid can go back and forth. So it's mostly like a what? I mean, something long like that, like a dog run. Okay, so you can make a dog run like that, but that's not really good for kids. So these extremes probably wouldn't be that reasonable. Okay, so something more in the middle. So that 40 is making more sense. All right. I like how it moves. That's so nice. All right, this one, Noah finds an expression v of x, open top box like we did yesterday. So here's the expression. All I'm asking you to do is two things. All right. What would be a more appropriate domain? So negative 1 to 5 doesn't make sense because we already agreed you can't have negatives. And if we go all the way out to 5, well, first of all, it dips down here, which means I'm going to have some negatives down here. And 5 up there, probably not so much. Okay? So let's narrow the gap a little bit. So probably between 0 and, we can't have negatives. So probably when it starts being negative, about 2.5. Okay. So my domain, just like we did before, so instead of using the word between, we put our x for our variable. Between means our two inequality signs, 0, 2.5. Okay? And then I want you to use your knowledge from yesterday. Find the actual volume, if we're using that as a domain, where you think it's going to max out. Okay? Don't say it. Just write a little sentence. What is the approximate volume for this box? The approximate volume would be. Just look at the graph, and I can see that my max is right about here. About 15. So 15 cubic inches. Okay. Questions? All right. Going to continue on with this idea of the open top box. We're just kind of replaying what we did yesterday, but instead of an 11 by 8.5, it's a 10 by 10. Okay. So think about the equation we had yesterday, the algebraic expression for volume, and just modify it a little bit. So instead of 11 by 8.5, so if you can look at your stuff from yesterday, do that. If you can't, you can look next to somebody else. And if you can't, in about 30 seconds, I'll put it up on the board. So those of you that didn't save your stuff from yesterday. All right. So it's the same formula, except instead of 10, or instead of 11, it's 10. And if it's 10 twice, do I really need to write the 10 twice? So we could take it to the, so if you just do shift, it's going to give you a little caret. That's the exponent squared. Okay? Where should we plug this in? Desmos. So let's go to Desmos. I wouldn't delete this one. Okay. Let's just hide it for a bit. I'm going to recenter my window. Okay. So x, 10 minus 2x, close it, squared. I'm going to keep it and duplicate it like I did before. And then change my x to, what was it, 3? Times 3. Times 3. Okay. About 48. Is that the max, you think? How would we find out? Look, okay. Let's see. If we just squeeze this down a little bit. Yeah, 48 is not the max. Look like it's pretty close to 75. Okay. This is kind of similar to the one we looked at yesterday. All right. So volume, I'm sorry, what was the volume? It was 48?
48.
And this is centimeters, so 48 cubic centimeters. If you just want to abbreviate cm for centimeters, that's fine. All right, the rest of the problems on this page are from Unit 1. Did we do Unit 1 of Illustrated Math? Yeah. No, we did not. We had our own Unit 1, 2, and 3 we were doing. So I'm not going to do the rest of those. That has to do with something called recursive sequences. So we are going to switch gears and go to the next do is look here and answer these two questions. You're going to hear this a lot throughout the rest of the next 2 months. What do you notice and what do you wonder? So all I want you to do is type. Just look and type. This is kind of like, this is almost like stream of consciousness writing, except it's for math. What do you notice mathematically and what do you wonder? So just take, I don't know, let's say 2 minutes. Okay, if you want to volunteer who you are, that's awesome. Okay, numbers are illustrated by a model, so we have a picture attached to it. Where am I looking for? Okay, second step broke the equation into its factors. That's important. We're going to talk about that. Multiple formulas for the same answer, different methods. They're all 329. Every single one was 329. What else we got? Basically the same thing. Ooh, factors of 329. Nice. Examples. We've got distributive property. And that's about it. Okay, so now let's take a look. All right. So there's no one right answer or wrong answer. So what do the green blocks represent? They're 100, okay? Those are 10 rows of 10. Oh, look. 10 rows of 10 is 10 squared. So one way that you could represent this, do you remember from elementary school, the 300 plus 20 plus 9? Anyone remember what that's called? What's it called? Expanded notation. When you expand a number by its place value, so we're taking it a little bit further than you did in elementary school, and we're going to take those place values and rewrite them as exponents or powers of 10. So 10 squared, 10 to the first power, and the little itty bitty ones, why is that 10 to the 0? Because 10 to the 0 is 1. Okay? All right. So now, kind of using that idea, we're going to create things called polynomials. And we're going to have a more formal discussion about polynomials over the next few days. But today, just trust me, that is a polynomial. 5x cubed plus 6x squared plus 5x. If I want to evaluate these at two different places, what tool do you think would work really well? Desmos, and turn it into a, not a graph, but a things like charts, got table. Okay, so put 5x cubed plus 6x squared plus 4x into Desmos, turn it into a table, and evaluate it at those two places. And we'll talk about it in about a minute. I'm going to change the name of this. We're going to also be doing 2.2 stuff in here. So let's see if slash works. 2.2 lesson. And I'm going to turn this one off. Scroll down here. If you made a new file, that's fine too. So somebody help me out. 5x cubed plus 6x squared plus 4x. Okay. And again, ignore the graph. We don't care about that. To make a table, gear icon, table icon. We don't need any of those. The default is it's going to start at -2. We want -5 and +15. Okay. Notice significant difference between -5 and +15. Let's talk about that a little bit. Why is that? If I put a negative and cube it, I'm going to get a negative. If I take 15 and cube it, I'm getting a really, really large positive. Okay. All right. Just put your answers in there. Just take them from the table and plug them in there. So the way I'd like you to show it is P parentheses -5 close equals, was it -495?
Yeah.
And then just put a couple spaces. P of 15. Let's use the proper terms here. So we're using function notation. Was that 18,000?
285.
Comma 285 because we're looking at a 5-digit number. Okay. All right. Using that idea, okay, of expanded notation. See if you can figure out how expanded notation of 5,000 plus 600 plus 40 equaling 5,640 is connected. How would you solve the equation? Don't say it, just write it. Need a little help? Maybe scroll to the top and look at those what do you notice, what do you wonder ones. In order to do that, if we look back up here, we took our expanded notation. What were we taking powers of 10? Aren't 5,640 just some number times the power of 10?
Yeah.
So what's our answer? 10. Okay, so x is just 10. Now I will show you more formally how to solve this a little later in the week. But right now, this is 5 times 10 cubed. That's 6 times 10 squared. And that's 4 times 10. Okay, no fancy process or method. I'm just using my expanded notation and my knowledge of powers of 10. Okay. Now we're going to take this and expand it a little bit more, make it a little bit more complicated. Okay. So we're going to know stuff. We're going to use stuff that you've done already. So we've done x plus 1 to the second power. We haven't done it too much, but we have done x plus 1 to the third power. And I want you to look at what's going on here. Okay. You have 11 squared is 121. 11 cubed is 1,331. You can confirm that on Desmos if you like.
Yeah.
But notice that the powers of 11 correspond to the coefficients in the polynomial. So this is 1, that's 2, 1. This is 1, that's 3, 1. So I'm actually going to do this a little bit different. Okay? So first I want you to find 11 fourths. Just take 11 to the 4th power in decimals. Okay? First we're going to go one direction, then we're going to go back the other. So find 11 to the 4th power. Using your knowledge of what you got in Desmos, okay, see if you can write the expanded version, the polynomial that's x plus 1 to the 4th power. Take a few moments. So first find 11 to the 4th power. You got to do that first. Okay? So 11 raised to the 4th power, 1,461? No, it wasn't, was it? Dang, that's harder, huh? 1,500 what? 15,000. 14,000.
14,641.
14.
I got 15 in my brain. I don't know. Okay. So now use the 1, the 4, the 6, the 4, and the 1, and rewrite x plus 1 to the 4th power. So instead of having to do all those multiplications, we now have a tool that will help us take this. Okay? So just look at the last two, and now see if you can figure out what x plus 1 to the 4th power is in expanded notation. Okay, so write the polynomial that is connected to x plus 1 to the 4th power. Oopsies.
Yeah, you should think about it. Yeah.
I want my tools back.
2, 1, yep.
What happened to my tools? Tools. Here we go. All right. No, what is my first coefficient? What is my first coefficient?
4.
What's my first coefficient?
X.
1, because my first digit in 14,641 is 1. So it's 1x to the power of 4. Where am I getting the power of 4? Because it's to the 4th power. Good news is everything's plus. So I'm going to put a space here between each one, but you don't have to. Okay? All right. My next coefficient, somebody else. 4. Okay? And all I got to do is I'm taking each of my exponents and reducing it by a power of 1. So instead of x to the 4th, it's x to the 3rd.
Why did it 0?
Okay. Space plus. My next digit is 6. 6x to the power of 2. Space plus 4x. And then plus 1 times x to the 0, which is just 1. That's it. Okay. It is kind of easy. All right. So now, see if you can figure out x plus 1 to the 5th power. Now that you kind of get the idea of how to do it, so go to Desmos, take 11 to the 5th power. Okay, and then after that, I'm going to show you a little shortcut how you can actually figure out what 11 to the 5th power is even without Desmos.
What do you do as a 0 when you're doing
Oh, my tools are back. Cool. I take 11 to the 5th power. So 161,051. I'm going to put that down first. 161,051. Comma, not period, not decimal. Okay. This one's a little harder because of the 0. Okay. So I'm going to put some spaces in here. So I'm going to start with x to the power of 5. Okay. I like putting spaces in because that way it separates each of the terms of the polynomial. We'll talk more about what that means. My next coefficient is 6x to the power of 4 space plus 1 or just x to the 3rd.
Yeah.
And now you have to think a little bit. I have a coefficient of 0. Do I write down that term? So I'm skipping x squared and going right to x. My next one's going to be 5 x squared, and last but not least, 1.
No one X.
Oopsies.
Yeah.
Sorry, get rid of the squared term, 5x, and just 1. Thank you. So we don't have a squared term. We skipped that one with x. Now, further, okay, there was a gentleman by the name of Blaise Pascal. So he was a French dude. Okay, and he created something called Pascal's triangle. So I'm going to show you a version of it, which is a really simplified version. Okay. So let's take a look at Harpalocodocus. I want the tools back up here, and they were there, and then I hit the wrong thing, and they went away. So that's okay.